In this chapter, we're going to be looking at a variety of different electrophile additions to alkenes. We're actually going to start where we left off in the last chapter with adding acids to alkenes, but now we're going to consider stereochemistry. And to show you why we need to consider stereochemistry, I'm going to show you an animation. If you want to look at this animation yourself, you can find it at ChemTube 3D. And what we see is we have this alkene right here, and it's reacting with HBr. Here's the hydrogen, here's the bromine. Now this particular substrate that we're starting with doesn't actually give stereoisomers, but it can still show the concept. So in the first step, the acid comes into alignment with the alkene, and we can see the reaction taking place. So there are the hydrogens going to that carbon, and we get the halide ion, and we form this carbocation. What I want you to see here is this carbocation is sp2, and it's completely flat. What that means is the top side and the bottom side are equivalent. And this halide ion can add to either the top or the bottom to add from two different directions and to potentially give us stereoisomers. So let's look at it adding just to one side. That happens, the halide adds, and you'll notice it went from trigonal planar sp2 hybridized to tetrahedral sp3 hybridized. So now in the product we form this sp3 center. So let's take a look at reacting this alkene with hydrochloric acid. The first step, we'll take our pi bond, draw an arrow to the proton, and then an arrow losing the Cl group. So this is a proton transfer step. And we now know because of Markovnikov addition, the hydrogen will go here, the carbocation will go to the more substituted carbon. So let's put our hydrogen there, positive charge there. Now what we have is this reactive site, the carbocation, which is sp2, and it's trigonal planar. Because it's planar, it has two equal sides. We have the front side and, of course, the back side. So when we go to add the Cl- nucleophile, it can add from either side. So let's do both. So if we add Cl- from the back, I'm going to represent that by a dotted line because we usually put back groups with a dash. And what we're going to do is we're going to keep these bonds of the ring all in the plane. Cl will be in the back, and that kind of pushes this methyl group out. So when we draw the product for this, we'll have the methyl out, the Cl back. Now we can do the same thing on the other side, but this time I'm going to bring the Cl in from the front. So if that comes in from the front, remember that's going to be a wedged group, so I'm even going to draw my arrow as kind of a wedge if I can. And now when I draw the product for this, I'm going to again keep all the carbons of my ring in the plane. The Cl will be on a wedge, and then this methyl group, which is the fourth group, will end up getting pushed to the back. And we get that product. So here we have attack from the front. Here we have on the left attack from the back. In this case, we formed products with a chiral center. And if you compare these two, at the single chiral center, the groups are inverted. These are enantiomers. They do form here in an even 1-to-1 mixture, so that we know is a racemic mixture. Now let's take a look at an example where we start with a chiral product. We have this chiral center right here, but our reaction is taking place at the double bond. So the reaction's only taking place here. What that means is don't touch this other chiral center, or don't touch the original chiral center. Only work with the functional group that's undergoing the transformation. Right, in our first step, this double bond reacts with the HBr and picks up a proton. So we end up putting, if you want to draw it in, the hydrogen goes right here. I'm just going to leave it implied. And then we get a carbocation on this carbon. We don't have any carbocation rearrangement here. It's secondary. Moving at secondary would not result in any net gain. At this point, now the Br- is going to attack the carbocation. But like we did in the previous example, it can attack from the front, or it can attack from the backside. And that'll result in two products. So let's draw both. Again, don't touch your original chiral center, so I'm going to leave this group as a wedge and not mess with it. If the Br comes in from the front, it will be on a wedge. And that's a new chiral center that we've formed. If we add it from the back, we'll draw a second product. I'll leave this chiral center alone. It comes in from the back, the Br is on a dash. And there's our new chiral center. In this case, one chiral center stayed the same, one was inverted. This is a pair of diastereomers. Usually you don't get a 1-to-1 mixture. Usually you have an unequal mixture. We're not going to get into the specifics of how to predict which is going to be the major, but it's going to be things like, since this group is out, that kind of partially blocks the Br from coming in to this side. So that means it's more likely to probably come in from the back away from this group. But you are going to get both products, just in an uneven mixture. One other thing I'll mention here, just in case you're not familiar with it, is this pH abbreviation. That is a phenyl group. And what a phenyl group is it's an arine substituent. Or maybe I should say an unsubstituted arine substituent. So if you have CH3 with a phenyl on it, what that actually means is it's this aryl group, or arine group. Although this ring has double bonds in it, these do not react like regular double bonds. So you don't have to worry about them undergoing these reactions that we're discussing in this chapter. Here's a problem that you should take a minute to try on your own and to see if you can draw all of the products with stereochemistry and then determine the relationships between the products. One thing I will go ahead and tell you is you're not going to get Markovnikov selectivity. If you look at both carbons of the double bond, this carbon has one hydrogen, this carbon has one hydrogen. There's no Markovnikov selectivity. Meaning it doesn't matter which carbon you add the hydrogen to, you'll end up with a secondary carbocation on the opposite side. So that means you're going to get more products than you normally would when you have Markovnikov selectivity. So see if you can write out the products for this. Let's start by drawing the carbocation intermediate. So let's assume first we'll add the hydrogen to this side and get the carbocation here. So let's draw that intermediate. H there, positive there. Now let's do the same thing, but now we'll add the H here to get the positive on the middle carbon. We're going to get both intermediates because one is not preferred over the other. Now think about the reaction of Br minus with each. So the bromide will come in and attack the carbocation carbon. And it comes in from the front and the back. So here, when it comes in from the front, we get the Br on a wedge. When it comes in from the back, we get the Br on a dash. Now let's do the same thing with our bottom intermediate. From the front, the Br will be on a wedge. And then it can also come in from the back. And the Br will be on a dash. So now if we look at the relationships between these. First, notice that in the top two products, we have a chiral center. The two products are non-superimposable mirror images, so they are enantiomers. The bottom two products, you might be quick to look and say, oh, well, they're mirror images, they should be enantiomers. But first, recognize this isn't a chiral center because you have two of the same group. Second, notice if you take one of these and flip it over horizontally. So if I flip this over, that Br goes from out to back and becomes this one. So these two are identical. Then if you want to know the relationship between one of the top products and the bottom product, we have the same formula but a different atom connectivity. The bromine goes from carbon 2 to carbon 3. So those would be constitutional isomers.